Hello, everyone. Welcome to the Tutte Colloquium for this week. I'm very happy to introduce Guoyin Li, who has come to us from Australia. So Guoyin received his PhD from the Chinese University of Hong Kong in 2007, and currently he is a professor in the School of Mathematics and Statistics at the University of New South Wales in Australia. His research interests include optimization, variational analysis, and tensor computations. So please take it away.
Thank you. I hope you can hear me well. First of all, I would like to thank for organizing my talks in here, and I'm very happy to visit Canada, in particular University of Waterloo. So today I try to present some of my recent research on proximal methods. Actually, I gave a talk in the optimization conference like a week ago, so I decided to choose a different topic in here because I don't know whether there will be overlapping in terms of audience. So in case you have been to the other talk, at least today you will also see something different, which is nice, I would say. So this will be based on joint work with Radu Bot in University of Vienna, and Min Dao, who was in UNSW like 2 years ago in the COVID time. And Ting K, if I'm right, Ting K was in Waterloo for some time as well. And our student, Pei Ran. Okay. So the agenda of my talk will be like the following. So essentially, I'm trying to give you a very brief introduction so that you will understand maybe why I'm interested in this area. And then I will give a very, very quick recap on non-smooth optimization, because many of the fractional programs we are interested are actually non-smooth, which means that some of the functions involved may not have derivative in the usual sense. Okay. And in particular, I'm going to focus very much on the single ratio cases because I don't have enough time to talk about the more complicated cases, but I will mention about in the future work later on. Okay. And then definitely when we propose the algorithm, we want to see how the algorithm converges, and that's where the fourth part. And I'm going to show you some numerical illustrations. Okay. So if time is permitted, I'm going to explain how you can design algorithm to converge into a stationary point in a stronger sense, but we will see whether I have time. Okay, and finally I can conclude. Okay, so that will be the outline. Okay, okay. If no one's stopping me, then I will just continue. Okay, so the fractional optimization I want to look at like the following, very simple. So we're trying to either minimize or maximize an objective function, which is described as a quotient of two functions. One is f, the other one is g. And over a possible constraint, which we call the capital S, at this moment, I didn't impose too much assumptions. Later on, I will impose specific assumptions. At this moment, all I require is that the feasible region S, over this feasible region, the denominator never take the value 0. Otherwise, I will be in trouble, right? So because I divided by 0 in that case, okay? And this is known as the single ratio fractional optimization problem. Okay, but in the literature, there are more complicated cases, which means that you can have a finite sum of this kind of fraction, which they call it sum of ratio optimization problem. But of course, you can convert this one into the single ratio cases, but sometimes you lose the structure of you can take into advantage. So that's why people first often focus on the single ratio cases, then they consider more general later on. Okay, and in the classical setting, maybe you will see it in many classical textbooks, and that's where the fractional kind of idea comes in. It's a very convenient trick in combining two conflict objectives into one. And this is a typical scenario in finance, for example. Say if you have two objects, say you want to maximize your return, at the same time you want to minimize your risk. And a typical way to combine these two conflict objects into one is that, okay, I can look at their ratio. So in here, say if I have, say, capital N many kind of project I want to invest, and I want to determine for each part of the project how much percentage I want to invest, then definitely the sum of this fraction, the sum of each one of the fractions should be 1. And each one should be non-negative in terms of fraction because we don't allow short cells. And the objective is just on the numerator, that's just the return, because this A means that for each I of component, AI is actually the amount of return for each project. So A transpose X is the return, and R is the reference. So on the numerator, it's the net return usually. So you want to maximize the net return. And at the same time, you want to minimize the risk, and there are many ways for representing the risk. But one way is just to look at the square root of X transpose AX. A is usually the covariance matrix. So in that case, this is the typical Sharpe ratio, probably you have seen in many of the classical textbooks. And if you look at this one, this is actually a fractional optimization problem. So very typical, classical scenario in terms of combining two objectives, convenient as one object. Okay, so that's the typical way. But of course, if you are familiar with optimization literature, you say, okay, why don't we do the weighted sum? Well, that's definitely sensible. Of course, that's very, very sensible. But of course, in that case, you need to determine the weighting parameter lambda. And in many cases, you need to tune it in the computation, and you need to interpret it as well. So the fractional approach, sometimes people refer to it as a parameter-free approach for if you have several objectives you want to achieve. And in that case, sometimes the optimal value can be linked with the optimal or the weighting parameter lambda, give some interpretation for that as well. So that's where, in the classical setting, where it comes up. Okay, but on the other hand, this is just one case. And the reason why I'm interested is because actually it pops up in several other applications, which I will mention two of them, which actually attracts my attention. And I'll probably go through the first one in a little bit detail, and the second one I will go a bit fast, okay? All right, because the second one is somehow similar. So let's see. So the first example I come across is it's probably quite popular. It's called the sparse signal recovery problem. So many of you may have seen it. So in this kind of application, you have a observation B, and often it's corrupted by noises. And you somehow want to match up the observation with a signal under a linear transform we call it capital A. So basically just trying to solve somehow a linear equation, right? So in some sense. But usually, in many cases, the signal we want to recover will have some specific structure you want to promote. And a very typical setting is that you know the signal under another transform has some desired sparsity. And a typical one is like this one. So suppose I have a piecewise constant signal, and I add noises, and I want to reconstruct my signal from the noisy observation. And this actually you can rewrite it as this AX almost equals to B with a suitable matrix A. And knowing that the original signal is a piecewise constant, that means that if you apply a discrete gradient operator to it, it's going to be sparse. So that's why you can have this MX has desired sparsity have in mind. So that's where the problem looks like. Okay, so I hope it makes sense. Okay, right. Okay, so far so good. Then if you look at the mathematical formulation, it's like the following. So basically what we do, we represent the sparsity in terms of the objective function, which we look at the cardinality function of mx. Okay, m is the desired kind of transform. And in the constraint, we don't ask somehow the AX perfectly match up with the observation. We just allow them to be close enough up to a suitable acceptance level, sigma. And somehow we know maybe a priori bounds for the signal between L to U in here. And if you put everything together, that's the mathematical formulation here. Okay? And usually we can assume without generality the origin is not in the constraint, because if origin is in the constraint, then x equals 0 is a trivial solution. So I don't need to care about that in that case. So that's why I can assume origin is not in the feasible region. And that's actually useful for me later on, you will see. Okay. So the problem is that somehow the cardinality function is discontinuous. You will see a graph very soon, and non-convex as well. But somehow it's a very delicate feature sometimes people make use of, but sometimes easy to miss, is that the cardinality function is scale invariant, which means that you multiply by a positive scalar, the cardinality doesn't change. Because if you multiply a positive scalar, those entries which take a non-zero value still take a non-zero value, so the cardinality actually never change in that case. Okay, so being the difficulty of this one, so the typical, what people do is that they find a continuous surrogate. So you can either do the L1 norm as a convex surrogate, or you can do a piecewise quadratic function, like a scat function in here, as a surrogate. So here, just a simple illustration. So in the one-dimensional setting, the cardinality function, when x is 0, takes the value 0, otherwise take the value 1. So it's a discontinuous, okay, and also non-convex as well. And the L1 norm becomes the absolute value functions. And the scat function is the one I plot in here. And you sort of see that the scat function somehow approximates the cardinality function better than the L1 function. And that's why some people prefer to do it. Okay, so I have one slide just to remind you about convexity, but I guess I can nicely skip on this one. But I just want to emphasize, in general, non-convex problem is often much harder to solve. Here I have a famous quote from Terry Rockefeller saying that the great watershed in optimization is about convexity and non-convexity. Okay, so, but I want to somehow mention one thing which may be interesting is that, so actually, sometimes, although non-convex model is harder to solve, but if you can solve it and nicely, then potentially you can get better accuracy. Here's one simple illustration. I'm just take the previous example I have in mind. So I have the piecewise constant signal. I add noises. I try to recover it. And if you solve it by the L1 regularization, which is a convex model, and it's doing very well, but still you see there's a misfit in here, so particularly in here, miss some of the supports over there. But on this one, we recovered it using the non-convex model. In particular, here I solve it as a scat model. So you will see that actually fits quite well. Actually fits better than the convex model. So basically means that if you can solve the non-convex model well, potentially you can get some advantage. But of course, I must admit that in general, solving non-convex model is harder. First of all, you need to choose the initialization wisely. And secondly, you need to design the right algorithm so that it converges to the right point as well. Okay, so that's what I'm trying to get at. Okay, but so far you haven't seen the fractional program, right? So let me show you what is that. Okay, so here's actually where the fractional programming comes in. So here's one very recent, relatively recent at least. They call it scale invariant regularizations. Actually, you can trace the origin from this earlier paper by Ernie and Jack Xing and Ying over there in 2014, but somehow was extensively studied, at least computationally, by this group, Rahami, Wang, Dong, and Lau. So it's very simple. So basically just the quotient of L1 and L2 norm. Of course, we exclude the origin in here. Okay, so, but it has several interesting features. First of all, it is scale invariant, just like the cardinality function, because you multiply a positive scalar. Then, because it's a quotient of about two types of norms, so it gets cancelled when you multiply it by a positive scale, right? So it's scale invariant. And it is bounded just like the cardinality function because in finite dimensional space, all the norms are equivalent, okay? But what I find most interesting is that numerically, they show that it performs much better than the L1 regularization, which they call Lasso model, particularly when the RIP condition, the restricted isometry property fails. Okay, so, but anyway, I'll show you a table on that. But because of the nice numerical experiments, so people have studied their theoretical analysis to see why it actually performs better. Okay, so, but at least I want to give you a nice idea about how the function looks like, the L1 divided by L2. Here I plot in 2 dimension, because 1 dimension is probably less of interest. The 2 dimension, which would be nice. And it's have this kind of folding shape. And if you look at it carefully, so particularly on the, I think this is x-axis, and this is the y-axis, you see the function takes almost the smallest value, which is actually taking the value 1 in here. I don't know whether you can see the number. So, which is perfect because for sparse vector in 2-dimensional cases, they are lies in the x-axis and y-axis. Okay, and that's what when we're trying to minimize it, you are promoting the vector somehow staying actually in the x-axis and y-axis, and they're actually bounded by square root of 2 because every norm is in finite dimensional space are equivalent. So you will see the maximum one is actually square root of 2 in here. Okay, so that's somehow it's like, but the important thing to notice for this function. It is not smooth, particularly on those places where the vector is sparse, particularly on the x-axis and y-axis. And it's also non-convex as well because you take any 2 points, draw the line segments, the function value actually lies above the function value on the line. It's over there. So it's a non-convex, non-smooth function. So if you look at its optimization model, what they propose, you just replace the cardinality function by this L1 divided by L2 norm and keeping the constraint unchanged. And here's one interesting thing that I told you that we are asked the feasible region doesn't contain the origin, and this is good for me because my objective is well defined in that case. Okay, and that's why I emphasized it before. So now this is actually a optimization model, and it's actually a non-smooth and non-convex optimization model. Okay, and that's one of my original motivation where it comes in. Okay, I hope it makes sense. Okay, so if you are okay with the model formulation, let me show you their numerical experiment, so which I find it very, very interesting. So in their numerical experiment, they compare with the L1 divided by L2 model with the L1 regularization model. And you will see that somehow in terms of the sparsity level of the solution, they do much better. And actually in terms of objective value, it's also much smaller. But what I find most of the interesting thing is that their CPU time taken for solving the non-convex model is even less than the one they solved for the convex model. And I found it puzzling initially, but when I look at the paper, and the main reason is that they solved the non-convex model using ADMM algorithm, where the subproblem actually has a closed form solution, which means the complexity is relatively low in that cases. But there's one potential drawback is that in the paper, they actually say that they actually don't know whether the convergence actually is true for the method they propose. And actually, they suspected that the method actually not always converges because when they plot the trajectory, which I will show you one graph later on, it's highly oscillating. Right? So that's why they suspected that indeed the algorithm, although works well, but in general it may not converge. That's what their conjecture. Yes.
Yeah, so you mentioned before the fractional is the same as splitting with a parameter. Mm-hmm. So why is this new model not the same as lasso with the correct parameter?
Okay. So So when I talk about lasso, I mean the objective function is just the L1 regularizations. That's what I mean when they compare with lasso. That's what I mean, the lasso model over there. So when they do the ADMM, they will replace x by u and let x equal to u enforced in the constraint and then do augmented Lagrange. That's how they do it. So it's a bit different in the way they solve it, I would say. Okay, does that answer your question? Okay, good. Okay, so so this is the first model. So when I see when they ask this question at that time, so my original motivation just to see whether I can propose somehow an algorithm, somehow, so on one hand, competing with the L1 divided by L2 model solving by ADMM algorithm. On the other hand, which I want to have some convergence guarantee so that I can, to be confident about what kind of the limiting point I'm getting at the end. Okay, so that's original motivation. So that's my first motivation. I hope it's okay. Okay, so this is the first, and then let me look at the second one. The second one is probably more classical one. So we have two classes of data, and we want to separate it. And typically, and you can have many ways for separating using different kind of criteria, but one of the typical one, or the popular one people use is the Fisher discriminant analysis. So what they mean is that they want to separate it in the sense that if the data belongs to the same class, then the within class variance to be small, which means that they somehow concentrated on the corresponding mean over there. But if they belong to two different classes, they want the between class variance to be large so that they can separate as much as possible. And you sort of see now I have two objectives. One is the within class variance to be small, and the second objective is I want the between class variance to be large. So I have two conflict objectives. Then this will remind you my first classical kind of situation. I combine the two objectives into one using the fractional tree, and that's where the optimization model looks like. So basically, it's almost like a generalized eigenvalue problem. So, but in the numerator, it's actually the within class variance we want to be as small as possible, and the denominator is the between class variance, and we want it to be large. So basically, we minimize the quotient so that we combine the two objectives into one. And of course, they are all homogeneous. We restrict it to the sphere so that everything looks nice. And at the end, sometimes we want to do a lower dimensional projection so that you can do classification efficiently. So we add a regularization, which is a phi x over here. Okay, so it depends on the choices of your regularization. But at the end of the day, this is actually a non-smooth and non-convex fractional program because Well, at least the constraint is already non-convex, right? So, and depends on the choice of regularization, they are all non-smooth in this case. So at the end, it's again a non-smooth and non-convex fractional program. So of course, these are not new in terms of optimization model, because at least you can find this paper, they propose what they call the truncated radial flow method for solving it. So, but the only thing is that they only show that it has local convergence, in the sense that if you initialize your points close enough to the true solution, then the method will going to converge. Okay. But of course, being a non-convex problem, you want to ask how close is close enough, and how do you determine it's close to a global solution, and that would be some tricky things to determine beforehand. So what people usually do is actually they do a heuristic beforehand, right? So they first solve a convex relaxation to get the initialization point, and then starting from the initialization point, they follow the truncated radial flow method. So it's a two-stage. It's going in here. Okay, so that's the two motivation example. Okay, right. So if you are happy with this one, now I can come up to my general question in here. So I spent quite a bit of time, but hopefully I can try to convince you that that's my motivation. I try to propose some numerical methods for solving at least some general, or at least reasonable general, non-smooth and non-convex fractional program. But the important thing is that I wish to have convergence guarantee as well. Okay, so that's the at least my aim. I don't know how successful I am on that, but at least I try it in here. Okay, so I'll show you how we can do it. Okay, so being the problems being non-smooth and non-convex, and you can ask, okay, why don't we try the typical tools in non-smooth optimization problem? Well, this is very sensible, but the common structure, solving non-smooth problem, often we need to take into account of the structure. And the typical structure is you can split the objective function as a sum of a smooth function and a non-smooth function. And we often require the non-smooth part to be prox-friendly, which means that its proximal operator can be evaluated efficiently. But this is not the case, at least for the L1 divided by L2 norm, because the L1 divided by L2 norm, its proximal operator, at least it's not known whether they have a closed form solution or whether it can be compute efficient or not. Okay, so that's why we probably need something additional, but some of the tools indeed would be useful for us. And let me quickly recall some of the tools we're going to use. One is the subdifferential. It's actually the analog of the gradient in the non-smooth setting. And the second one is the proximal operators, which is a generalization of the projection operators. Okay, so I will be quick on these two. So for the subdifferentials, usually people start with the most simplest case, which is the convex subdifferential. It is just a kind of object that collects all the elements of the slope of the linear function that lies underneath of the graph of your original function and interpolate it exactly at the point x0. Okay, so basically it means that if you look at the graph, this is my non-smooth function f, but it's convex. So I can draw a lot of lines that passing through the point x0 and fx0, but lies underneath the graph of the function. And if you collect all the slope of these lines, and that's the convex subdifferential. Okay, so that's what it means over there. But of course, because many of our functions are non-convex, so this probably would not be enough for us. But at least one of the nice things is that for the convex subdifferential, if your point is a global minimizer, then it means that you just need to check whether the origin is in the convex subdifferential. Okay, so when you move to non-convex setting, so we enforce somehow a local version of the convex subdifferential, which means that we want to preserve that if f attains a local minimizer at the point, then 0 is in the subdifferential. And the way we modify it just to ensure somehow this quotient in terms of lower limit is going to be bounded below by 0. Okay, so unfortunately this definition of subdifferential called Fachet subdifferential is not stable or not robust in the sense that if you have a sequence that approaching to a given point and you take a sequence in the subdifferential, their limiting point may not be in the subdifferential of the limit x over there. So which means that when you design algorithm, this is a bit unstable. So what people usually do is that they robustify it, they call it limiting subdifferential, which means that they collect all the possible cluster points of the nearby points and also the nearby subdifferential from the Fachet subdifferential. And they collect all the possible cluster points and they form the bigger set, which they call it limiting subdifferential. So that you will collect all the possible cluster points over there, so you will keep the robustness property. Okay, so that's what they, okay. So in that cases, you can have the different kind of version of stationarity. You can ask for 0 in the limiting subdifferential to call the limiting stationary point, or you can call the 0 in the Fachet subdifferential to be the strong stationary point. Okay, so you have different types of stationary points. So the limiting stationary point probably is more widely adopted in the literature, but the second one is actually has attracted more, I guess, interest recently, and let me explain why. Of course, this is a stronger one because the Fachet subdifferential is a subset of the limiting subdifferential. So if you're asking 0 in this smaller set, it's a stronger kind of conclusion. Okay, so and in particular, why people are looking for the stronger version is because recently they have found that for many problems with very much specific structure, the stronger stationary point is much more closer to local minimizer or sometimes global minimizer as well. Here's one result, which I just as a representative result. So if you want to say do a piecewise affine regression, which means that say xs is the input, ys is the output. So you want to, originally you want to do a linear fitting for the input with respect to the output, but sometimes this is not possible because things are, in general, can be nonlinear. So the first easiest thing people would do is that they want to fit the output ys as a piecewise linear relationship with respect to the input. That's why they have a maximum of k-many linear function in here, and they want to match up to the output as much as possible, so they minimize the least square in this set. Okay, so that's what they do. And what they find is that if you can propose an algorithm that solves to a strong stationary point, you end up with a local minimizer, which means that it cannot be a local maximizer, which is something is not what you want. Okay, which is I find it interesting. And actually, they can extend this one to some sort of neural network structure or with the ReLU activation function as well, but with some specific structure as well. But I'm not going to go into detail. But I just want to emphasize why they want to look for a stronger version of stationary point over there. Okay. So, all right. So here is a simple illustration which they show that empirically. So they have two types of method. One, the subgradient method, which is just converting to a usual stationary point. And I guess for you, this is the orange dot, is the method that converges to the stronger stationary point. And you see that empirically, the stronger stationary point often has much lower objective values, and which means that empirically, at least you can sort of see that a converge to a stronger version will bring you some benefit in terms of objective value at least. Okay, so the other tools I'm going to need is the proximal operator, which is just very simple. Basically, it's an operator that for a given function f, this should be 2 power Rn in here. Basically, for a given function f, we regularize it with a quadratic function, and then we take the solution set of this parametric family with respect to a given v here, and the corresponding set, we call it proximal mapping, evaluated at the point v. Okay, and this is what we call the proximal operator. It's so in particular, if you think about f is the indicator function, which means that of a set, which means that if x belongs to the set, that's 0. Otherwise, it takes infinity, then this reduced to the projection mapping. So it's essentially it's extension projection mapping. Okay, so you can evaluate many of the proximal operator for some of the function we have seen before, but here at least is a typical method for solving non-smooth optimization problem, which will borrow some of the idea in here, which will be the proximal gradient algorithm. So what they do is that they're assuming the non-smooth function can be split into the sum of a smooth part and a non-smooth part. And then what they do is that they first do a gradient direction on the smooth part, and then they evaluate the proximal operator on the non-smooth part. And provided this non-smooth part has a nice evaluation for the proximal operator, then this proximal gradient method can be implemented quite efficiently. Okay, so, but there's a nice interpretation of the proximal gradient method, which we're going to use very soon, is that you can interpret it as a majorization and minimization algorithm, which means that what they do essentially, just at the given point xk, the way they generate the next iterate is that at the point, they construct a quadratic majorization to dominate the smooth part, and then they minimize the surrogate of this one, add up with the non-smooth part to generate the next point. And in terms of graph, that's what happens. So suppose you have a given point xt in here. So what they do is that they construct a majorization in here, and then they minimize this majorization. They get the minimizer, which they name to the next function. But being the majorization, you will see the function value at this point should be smaller than that, so your function value definitely get decreasing when you iterate it once. That's how the proximal gradient method is actually constructed. So it's a majorization, minimization kind of algorithm. So you construct a majorization as a surrogate, and then you minimize this surrogate, and then you iterate. Okay? So once you see this one, then the way we do it for the fractional program would be somehow analogous. Okay? And let's see how we do it. Okay? So let me record you the fractional program. Okay? It's of like the following form. So we minimize a quotient of f divided by g, and x is in the feasible region S. And of course, I cannot do arbitrary things. I must impose some assumptions. And let me be specific about the assumptions. Okay, so here I will going to have 3 standing assumptions. So they may be a little bit wordy, but I want to say before I go into that, so all the motivation example I have in mind would going to satisfy them. Okay, so the first assumptions, somehow similar to the proximal gradient setting, I'm going to assuming my objective can be split into the sum of the smooth part and the non-smooth part. And I'm going to, later on you will see, I'm going to assume the non-smooth part actually is prox-friendly as well. Okay. And somehow my denominator g, I'm going to assume it to be continuous and weakly convex. By weakly convex, I mean if you augment it by a quadratic term, you can make it convex. So in particular, convex function must be weakly convex, and also any quadratic function will be weakly convex as well. So, and the last one is typical in the fractional program literature, which means that f and g has some suitable sign structure. Okay. So, but if you think about, for example, my motivation L1 divided by L2 norm, so for the numerator, the L1 norm actually will be the non-smooth part, which is prox-friendly. And my denominator is L2 norm, which is convex, in particular weakly convex. And of course, they are non-negative as well, satisfy the sign structure. So at least for my simple motivation example, these are all satisfied. Okay, so that's what I'm trying to say. Okay, so as I mentioned, you could have different versions of a stationary point. You could have the typical stationary point argue that 0 is the subdifferential of the objective function augmented with the constraint function over there. And you can even use the fractional rules to compute the limiting subdifferential to ask for the lifted stationary point. And you can ask for the strongly lifted stationary point, which actually has something to do with the strong stationary point I mentioned before as well. Okay. Okay, so I have an example, quick example just to show you that at least for this one-dimensional non-smooth fractional programming problem, the lifted stationary point and the strong lifted stationary point are not the same. And indeed, in this case, the strong lifted stationary point are exactly those local and global minimizers. So basically just to show you that there are cases where the stronger version can actually have some benefits. Okay, so, okay, now let's see how the method looks like. Actually, the converters could be a bit tedious, but in terms of idea is very simple. And let me explain. And the idea is somehow traced back to what we call the Dickenbach method. And it's a very popular approach, actually has been done, maybe can be dates back to 1970s, and you can find it in Scheiber's nice review over there. And let's see how it works, okay? And the idea of the Dickenbach method is somehow we're trying to transform the fractional programming to a parametrized version of non-fractional cases. And it looks like the following. So suppose that we know the true optimal value of your fractional programming problem, just suppose for a moment. And in that cases, you can actually rewrite just by definition that the point X bar solved the fractional programming problem if and only if the X bar solved somehow this non-fractional programming problem. So you just can check it by definition by rearrange the denominator a little bit. Okay, but probably this one is not practical because, well, if you're trying to solve this non-fractional optimization problem, you need to know the true optimal value beforehand, which is not practical, right? Before you solve it, how do you know the true optimal value? But we can approximate it, and that's what the decombug method. So the decombug method saying that, okay, suppose you have a point xn. For the given xn, I plugged it in to compute the function value at the point xn. Then I solve this parametric function or parametric optimization problem. Then I generate the next iterate. And hopefully you can imagine if things works nicely, say xn converges, and then you can sort of see when n goes to infinity, this one will approximate the original true optimal value theta bar, and then you get what you want. And that's what the decombug method is. Okay, but I must emphasize that decombug method still can be very hard to solve. For example, in the case where it's L1 divided by L2, then when you convert this one, you actually get L1 minus a constant times L2 norm, which is still not very easy to solve. And of course, you need to solve a parametric family of them as well. Okay, and what is even, I guess, more harder to analyze is because the current analysis is basically limited in the smooth setting, and they also require somehow the function has some convexity as well. Okay, so, and let's see how we can do it in this case. And somehow the idea is very simple. We are again going to use splitting algorithms idea because you will see the major difficulty in using the decombug method is that the f and g is going to couple in your subproblem. So we're trying to tackle them individually, and hopefully we can solve them easily. Okay, and that's the splitting idea comes in. So let me just quickly show you what you can do. Although the analysis is very tedious, but the idea is very simple. So let me just rewrite the decombug method in here. So remember, I asked for my numerator can be split into the sum of the smooth part and the non-smooth part. And this is actually what the theta n, I just write it out explicitly. Okay, so what we do is actually say, suppose I'm given two approximation, un and vn for the current iterate xn. So if it is too complicated, just think about them as just the current iterate xn. Okay, so for the smooth part, so what I'm going to do is that, like the proximal gradient, we're going to replace it by a quadratic majorization, which you can do it by using the Lipschitz gradient of the smooth part. And for the numerator, we're going to approximate it as a linear function using an element in the limiting subdifferential. And for the non-smooth part of the numerator, I never change it. I just add a proximal term to make things work nice. Okay, so at the end of the day, this is the algorithm. So the first part, remember, this is actually the quadratic majorization for the smooth part. And for the non-smooth part of the numerator, I never change it. I keep it as it is. And what is the last term? So the last term is because we use the linear function to approximate the denominator, and we add the proximal term, you can complete the square, and that's exactly the last term in here. Okay? But if you look at it carefully, so because the iterate xn is given, so this is actually just a quadratic function. This is a quadratic function. Ultimately, the subproblem reduced to computing the proximal operator for the non-smooth part augmented with the constraint set. Right? So in particular, in the two motivation examples we have in mind, they actually either has a closed form solutions, or you can convert it to a convex quadratic programming problem, which you can solve efficiently. For example, you could, in the second case, if you convert it to a convex QP, you can look at its dual problem and solve a one-dimensional dual problem in that cases. Or you can reformulate as an eigenvalue problem and then call the eigenvalue problem solver as well. Okay. But of course here, as I mentioned, you can actually do an approximation, which means that you can potentially, you can incorporate the momentum algorithm into here to speed up the computational experiment, right? So and that's the algorithm. So in terms of construction of the algorithm, it's not very difficult. So basically it mirrors the majorization and minimization techniques of the proximal gradient algorithm, but combining with the decombug method, and that's all it is. Okay. Right. So And in terms of convergence analysis, so here's what we have. So it's a very typical assumption. If the lower level set of the initial point is bounded, then the sequence going to be generated will be bounded, and somehow every cluster point is going to be a lifted stationary point. Okay. So here I'm hiding a lot of technical details in here, in particular the choice of the parameters, so that you can do somehow a momentum or restarted vista and in the non-convex setting, and you can prove the convergence over there. So this is a bit tedious over there, but somehow the idea is to construct this decreasing sequence, and then you argue that somehow the function, the algorithm, when it evolved, then somehow this constant actually gets decreasing, so that you can control the convergence. Okay, so far I only tell you that the sequence is bounded, and any cluster point is a stationary point, but I haven't told you whether the sequence convergent or not, because somehow you can jumping around between 2 points, right? So they are still bounded, right? So that's where you probably expect it. That's where the KL property come in. Okay. So the KL property is, a widely studied property these days. So essentially, it's the property about the regularity of a function, but somehow it's satisfied by a wide range of functions, like the semi-algebraic function, which is like a maximum or minimum of finitely many polynomials. Okay, so what it says is that, say, we are given somehow a nice function, we call it desingularization function. It's just one variable. It's actually increasing, and usually it's concave as well. Okay, so what it says that if I take the desingularization function just to be the identity, and you can ignore the v dash in here, the derivative becomes a constant. So it basically says that 0 to the subdifferential is bounded away from 0. So basically means that it's like the absolute value function over there. Okay. So then the general case basically means that if you do somehow a nonlinear transform, you can always reduce your function to a function like the absolute value of x. So that's what it means geometrically. But it turns out that it actually is satisfied by a wide range of functions, which is like the semi-algebraic function. Okay, so, and if you impose this KL property for this suitable function over there, then actually you can now prove that the whole sequence converges. Okay, so in particular, this KL assumption is going to satisfy by a lot of cases, in particular for this motivation example we have in mind. Okay, so if you want to say a little bit more, say here we just say the convergence. Then if you want to say the convergence rate exactly, then you need to dig a little bit more on the KL property, that's where the KL exponent comes in, and which means that if your desingularization function takes this exponent form, and somehow this exponent completely determines the corresponding convergence rate in here. Okay, and that's where we're trying to estimate this KL exponent, so that you can use this one to determine whether the algorithm you propose is converges maybe linearly or sublinearly, or maybe sometimes just converges in finite step. Okay, so we have a bunch of estimation about the KL exponents. So there's a lot of existing results in here, and then we're trying to also contribute in the direction that by particularly looking at some very specified structure problem that arise in the regularization of optimization problem. Okay, so but at least let me show you for these two particular fractional models, we actually have a very explicit KL exponents. In particular for this one, for the L1 divided by L2 model, and actually you can calculate the KL exponent is exactly 1/2. And the way we do it is to basically use the tools we derived before to reduce the case to the quadratic function and use the KL exponent for the quadratic function. And for this generalized eigenvalue problem with regularizations, we also derive a KL exponent which is 1/2. Okay, and as a consequence, then you will see that the algorithm we propose actually in here enjoys a linear convergence rate. Right. Okay. So these are the convergence analysis in here. So if you are okay, I can show you the numerical experiment now. Okay, good. So let me show you the numerical experiment for the two motivation example I mentioned before. Okay, so first of all is the L1 divided by L2 norm. And actually here I just show or illustrate with a very specific cases, which basically the reason is that we're trying to compare with what is exactly was done in the previous paper, which they argue for that it's a noiseless cases, which they require AX to be exactly matching up the observation B over there. Okay, and they generate the cases by the oversampled discrete cosine transform, and in particular, that involves somehow a constant which they call the capital F. And hopefully you can see when the capital F is large, then this one's all somehow close to 0, which means that all the columns of this AJ are similar. So in that cases, the coherence level of A will be actually very big in that cases. Okay, so which is often the case when the L1 regularization actually doesn't work well. Okay, so basically we are interested in the case when this number F to be relatively large, and rather than the case when it's relatively small. Okay, so let's look at the cases. So we basically use the same setting as the paper I have mentioned before. So we look at, so what we do is that, okay, we generate somehow a ground truth with a specific sparsity, and then we normalize it to make the bound to be -1 to 1, and just like them, and then we set the capital F equals to 10, exactly as what they did, and then we see how the method works. Okay, so we use the same termination criteria, and remember when we use our algorithms, our subproblem becomes a quadratic programming problem. So in the paper, we actually didn't do anything, extraordinary. We just used the commercial solver Groovy to solve the quadratic programming problem there. Okay, when you compare with the ADMM algorithm they proposed, so actually we get the same, the same sparsity level in terms of solution and very similar objective value. But I must say that we actually takes a little bit more time comparing to that. Okay, and I guess the reason is that actually here we just use the commercial software Groovy. We didn't do extra kind of effort in here. And actually later on, one of my students dig into that and he proposed to solve the convex QP using ADMM directly, then you can actually get much better CPU time in here, so that in that cases. But one thing I want to remind you is that the ADMM method they proposed doesn't have a convergence guarantee. So in particular, if you plot the trajectory out, in the first, 100 iteration, it's highly oscillating here, probably hard for you to see. But at the end, it settled down a little bit, but because of the highly oscillation, so they have very much difficulty to prove the convergence. Okay, so that's what the reason is. Okay, and so this is what I say, the ADMM algorithm doesn't have a convergence guarantee, at least at this moment. Okay, but for the second motivation example, I look at the sparse generalized eigenvalue problems. Okay, and again, we are going to take the same test setting with respect to the paper over there, although in the paper we also do random kind of initialization point as well. But here, just for comparison, we do the same initialization point and use the same kind of termination criterion as them. And you will see that in here, we actually get a better sparsity level and also a slightly better objective value, and we use 2/3 of the time and less iteration as well. Okay, so here's just a simple plot, and which is the proposed algorithm, which is the blue curve, and this is the truncated rate flow method they use. And maybe what is more interesting for me is that in here we actually get a global convergence and with a linear local convergence rate, where the original algorithm they propose only have local convergence, which they don't know the rate as well. Okay, so I think for me it's probably more important. Okay, so let me just check the time. Okay, so maybe I should mention that, so actually you can, so I mentioned that there are various versions of the stationarity, and actually you could propose a stronger version of a stationarity, and you can actually modify the algorithm accordingly so that the method converges to a stronger version of this fractional program. And let me say how this stronger version looks like. So the typical stationary point we are looking at is this lifted one, which means that 0 in the difference of these two sets. Basically, it means that you will have one common element in the first set and the second set. But the stronger version actually requires whatever in the second set is an element of the first set. So that's why it is a stronger. Okay, and actually, if you rewrite it a little bit, it basically means that 0 is in the Fouché subdifferential of the corresponding objective function. Okay, right? But you could design algorithms so that it converges to these stronger versions. And let me just briefly mention how you can do it. So here we need a little bit more structure. We need the denominator, basically here, to take the form of the maximum of finitely many weakly convex function. And the way we do it is very simple. You just need to, one observation is enough. So remember, this is actually what we want to have. We want the second set is a subset of the first set. And if you rewrite this one a little bit for the first computer limiting subdifferential, all you need to do is just to argue that for any active index set, whatever in here is actually an element of the second set in here. Okay, so now you see if you compare to the lifted stationary point we had before, the only difference is that you replace whatever in the left by this gradient of GI, which is the every maximum of GI for each GI in here. So what we do is actually just exactly like what before. You just whenever you see the subdifferential of G, you replace it by the gradient of GIN. Okay, and at the end, but of course you need to take the best out of it. So that's why potentially you're going to solve many of these subproblems in here. So the computational cost is a little bit higher, but the convergence rate is actually similar. Okay, so now I think I should conclude. So I'm trying to convince you that somehow non-smooth fractional program is an interesting problem to look at. And in this talk, I basically focus on the single ratio cases. And I talk about some proximal kind of method and with convergence guarantees. Okay, and of course, these are just very, very preliminary work. And there's a lot of maybe potential future direction to go. First of all, I only mentioned the single ratio cases. And you might be wondering what happens for the sum of ratios. And actually, there could be many ways, but at least recently we did one approach, which is we use somehow what we call a quadratic transform to transform the sum of ratios into a single ratio cases and then to compute it. And in the second one is that when we propose algorithm for the strongly lifted stationary point, we need to solve the subproblem multiple times. And when the dimension is high, this actually could be very time-consuming. So, and one of my students trying to look at the randomized techniques, hopefully to reduce computational cost. And of course, in the literature, there are many other approaches. For example, people have used the branch and bound methods. And there are also very recent, like moving ball approximation, particularly Tinker has one algorithm of that. So I haven't compared the methods with them as well at this moment. So the comparison would be interesting. So finally, I think I should stop with the reference. So basically, the paper I presented basically is the reference, I think, 6. And the 7 is the sum of ratios I briefly mentioned. And I think the 8 and 9 are the somehow the motivation examples I mentioned before. Okay, so I think I probably should stop in here. And any questions and comments will be very welcome. Thank you.
Hi, thanks for the nice talk.
Thank
so
you.
The sharp ratio example that you gave at the beginning, that's I think a hidden convex problem. And so if the problem is actually convex but hidden, then does your algorithm have any special properties or?
Yes, actually, I think you're right. And first of all, if I remember correctly, even goes back to 1980s, if I remember right, there was a paper by Zhongxi Peng who actually showed that for these sparse ratio, okay, that's the very first few pages for this this one, for this a sharp ratio problem. First of all, I think in Zhongxi's paper, he linked the optimal value of this one to the weighted parameter. I give an interpretation of that. And also because we require A to be positive definitely, so this is actually a fraction of, actually, well, it depends on how you view it, but essentially you're right. So this can transform into almost an equivalent convex problem to solve. And actually, you can solve it much more efficiently by using these techniques in here because those techniques didn't exploit the convexity in here, right? So So, but I think one thing I like is that in this case, in particular, you have a nice interpretation over there, I think. I hope that it makes sense to you.
Other questions?
Yeah, thanks for the nice talk. And yeah, it's called a pseudo-convex function.
Yes.
So yeah, I had two questions. First of all, that ratio that you had, the L1 over L2, has anybody used L1 over the geometric mean instead of the L2? And then you would have a pseudo-convex.
Very good question. So I haven't seen using other geometric mean or something, but I have seen maybe other very natural extension. There are people looking at LP divided by LQ. I have definitely seen that. And they have also looked into the matrix setting. In that case, become, I guess, the nuclear norm divided by the Frobenius norm in the matrix setting. I have seen that as well. But I haven't seen the geometric mean, things like that.
So I guess it's mysterious to me that, so you're getting convergence, but like you say, it's a non-convex problem. And I thought, does Dinkelbach need a global minimum during the algorithm
in
to
the
get
subproblem,
convergence?
the Dinkelbach method often requires a global minimizer. But in here, so here is actually in the subproblem, basically you just after for, in some sense, in the subproblem we are solving, we also ask for a global minimum because we solve for the proximal operator. So if you look at that carefully, let me just go down to that subproblem here. So here we also solve a global minimizer. But what we did is that because we approximate it by a quadratic function, at the end of the day, it becomes the proximal operator of the non-smooth part. But still, it's a global optimizer for the subproblem. But because of the L1, L2 norm, so the Fn, the non-smooth part, becomes the L1 norm. So that makes everything becomes solving a convex subproblem over there. So basically, we linearize everything, reduce the subproblem into a convex one, and then you iterate it. But the price we pay is that the limiting point here we sacrifice as a stationary point at the end. So that's probably the difference over there.
If there's no more questions, then let's thank Guoyin again.
Thank you.